This is now Y. Do you not know that from when we talked about it in the first 2 weeks? Guess what? This is going to become a very difficult question to answer. And that's only the first one. Okay? This is why we talked about it. This is why I told you that you needed to learn it and practice it. So they have the same molecular formula. So we follow our flow chart, to our yes, which then says, oh, great, we still have A and B. So we move to the next question in that. Are they superimposable? Superimposable is a tricky concept to get. Okay? It is overlaying two things so they occupy the same space. So I've got 3 pens, which I'm attempting to hold up. Are they all superimposable? I heard someone say no. Why are you saying no? If we look at the middle one, the blue one is a different shape. It does not superimpose on the others. If I tried to overlay that, number one, they're different lengths. So they clearly can't superimpose. But if I take the green one and the purple one, same length, same shape, same manufacturer, they superimpose. Okay? We run into 2 words that pop up with this: superimposable and superposable. Is there a difference? Yes. Yes. Does that difference mean anything with respect to solving these? No. And I don't remember which one's which. Superposable is that they can literally occupy the same space. Well, no 2 objects can literally occupy the same space. So it's kind of a dumb statement to make. Superimposable is that if they could occupy the same space, they would. So we're splitting hairs on the definition. Okay. Can they occupy the same space if they were allowed to? Yes, that's what we're asking. That's superimposable or superposable, whatever you want to call it. Okay? So, if we look at structures 1, are they superimposable? No, there is no way we can get those to superimpose, so we then move to the isomers category, which is not a bad place to stop, except there's another question. So we move to the next question. We run into the same atom connectivity. Right? The words, I use them sometimes. I should reset eventually. Nomenclature. There's the word. That's the word I'm looking for. It was a hard word. Okay. Same atom connectivity. The other way that we could reference this, at least at this stage, is do they have the same name? If they have the same name, then they have the same atom connectivity. They'd be stereoisomers. Would I name those 2 structures the same? Okay. This goes back to our nomenclature and how we approach that. We'd have to find the longest carbon chain. If we identify the longest carbon chain in the first structure, how many carbons do I have? 4. The longest carbon chain in the second structure? 5. Okay. Let's address the same atom connectivity. So just for S and G, instead of saying 5 carbons, let's just say arbitrarily it has 4 carbons in its chain. Okay. Here's our atom connectivity. I have an extra carbon. Where is that extra carbon connected in the first structure? Position 2. Where's the extra carbon in the second structure? Position 4 or 1, doesn't really matter. Okay. Are those numbers the same? No. So they don't have the same atom connectivity. We've connected different atoms to each other. Okay. Nomenclature works sort of the same, but we run into exceptions with that when we pick up enough knowledge. Okay, so no, they don't have the same atom connectivity, so they are then structural isomers. Kind of, sort of?
Yeah.
Okay. Number 2. They are identical. So we would follow through our flowchart the same way. A and B, do they have the same molecular formula? Yes, they do. We would then encounter this question, superimposable. Okay. Those don't look like they're superimposable. Okay? Said a different way, can I superimpose these two pens? Really? That doesn't look like they superimpose. Oh, that's right. I work in 3 dimensions, and in 3 dimensions I can turn that, and now they superimpose. Okay? What is special about that first structure, or the second, let's just say the first structure? They are all sigma bonds. And what did we learn when we talked about molecular orbital theory with sigma bonds? They can freely rotate. And if I rotate about one of those bonds, what ends up happening? It can become superimposable. If at any state they are superimposable, then at all states they are superimposable. And the answer to a superimposable is yes, and we are now identical. This is exceptionally tricky because when we look at those structures, we might initially say they aren't superimposable because of how they were drawn. This goes back to identifying a species. If you were to all draw me right now, okay, we did it really, really simply, okay, you would probably draw something along these lines. Me and stick figures. Let's just, there we go. Okay. You would probably draw at least a face and presumably the rest of me. But if I turned around, now what do you see? Are those two structures the same? They're representing the same thing, but from a different perspective. Okay? The same thing is happening with our organic structures. We can change our viewpoint on the molecule to make it look different. That doesn't change its inherent nature. Is that exceptionally tricky and difficult to process? Yes, because you are working in 2 dimensions, which is why you need a model kit to work in 3 dimensions so that you can see those relationships. Yes?
But in molecules, if one is slightly differently positioned, does it become a completely different compound?
So, what we run into on our superimposables, the superimposable, if they are superimposable, it will always be identical. Yes, it will always be identical. There is no exception on that. What you might be getting down to into the same atom connectivity and looking at where in space something is located. Okay? And that's a trickier statement. That statement we don't want to answer yet. Okay? And you are correct. That is absolutely true. Okay, but we don't want to deal with that yet. That's chapter 5. We probably want to wait till after exam 1 to talk about that. Okay? So let's do the simple stuff first, get a basic outline, but then absolutely you're right, we have to open that can. Okay? For those of you wondering what she's asking about, let's put it this way. If you drew me, my shoulders face forward, right? Okay? We could also draw me in such a way where one of my shoulders faces the other direction. Not I turn my arm backwards, but literally the shoulder faces the other direction. Is everything still connected the same?
No.
Yeah. My shoulder is still connected to my upper body, but is how my arm functions in space different? Yes, that's what you're getting at. Does that change my functionality? Well, if you wanted to come up and shake my right hand, you wouldn't be coming up to my face, you'd be coming up behind me. Okay? So yes, that changes drastically how our molecule interacts with the world, and we would see that person, if it happened to walk in the door, as a different person. Okay? Technically not different, but as a stereoisomer. Okay? So, this was the slide that I was trying frantically to find earlier. This summarizes all of our nomenclature. Okay? If you get all of this and able to manipulate this, you should be able to answer any nomenclature question from here to the end of the semester, or end of the year of organic chemistry. Okay? So there's a lot of content on here. Okay? It is not in the slideshow immediately. It's part of a different slideshow. I'll make sure the slide becomes available, okay, so that you have access to it. Okay? We've got the number of carbons. I almost got all the color coding right. The number of carbons outlined. You should know up to 10. More than likely, non is as far as you would need to, well, more than likely, oct is as far as you really need to go. Okay? The non and dec just aren't that much extra effort, so I'd memorize them anyway. Our functional groups, we will change the ending of our name based on the functional group present. So if we have an acid, we'll call it an oic acid. Why is the O in quotes? Sometimes we don't want to include the oic and it just becomes ic acid. It depends on the rest of the bulk of the name. Okay, so you might see it as oic acid. You'll notice with the oic acid, I call that highest and the halides are lowest. What are we referencing there? The priority of the functional group. We will be talking about priorities that has nothing to do with naming. The priority of the functional group is something entirely separate and different from that. If we have multiple functional groups in our structure, okay, that means we'd have to have multiple endings on the same name. Well, how many ends do you get in a name? You get one. That's it. Because it's a straight line. There's only one end. So how can we specify those extra functional groups if I have a whole bunch of them? We have to change where and how we reference those names. That's what those arrows are kind of showing through the middle. If it is the primary functional group, it's the name on the left. Okay? Notice that there's no dash. Alkane, there's nothing coming after it. We end with the E. Alkyne, nothing coming after it. But what if there's a higher priority functional group than the alkyne? Then there's a dash because I need to specify more information about that higher priority functional group afterwards. Okay? So that's the intent of what's happening within that. Okay? Your functional groups, upper right-hand corner, suffix, highest priority. Okay? We have to rank them. That's what that whole arrow thing is trying to describe. Rings, it is stupidly common for students to miss out on rings. You'll see a ring structure that has 6 carbons and you go, oh, that's a hexane. And then you're trying to name the rest of it and go, I don't know. It says it's a dimethylhexane, but I don't know where to put the methyls. It's because it didn't say dimethylhexane, it said dimethylcyclohexane, which then means the methyls are located at position 1 by default. Okay? So you have to recognize that cyclo changes your system. So we have to be a little bit careful and make sure that you look for that cyclo word. Don't make it cyclic if it doesn't say cyclo. Conversely, if it says cyclo, don't make it a straight line. Okay? In blue, we have our bulk rules on how to put it together. Find the longest carbon chain that contains your highest priority functional group. So you need to know your functional groups. Okay? Identify the highest priority functional group and all the substituents. Define the location for everything identified in step 2. Put the name together in alphabetical order. Does this summarize all of the rules for nomenclature? No, not even close. All the rules for nomenclature come in a book that's roughly 300 pages. Okay? You don't want to read it. The textbook author doesn't want to write it. Okay? So if you want to find all that extra information, you can. You can look online. You can look it up. I'll try and find the link for you so you can look at all the fancy rules. Okay? For the most part, the rules listed here will get you to the appropriate name. Yes, there are exceptions. Big one is already on the slide. Ring structures mess with the entire nomenclature system. Okay? So we have to be kind of careful. This is where practice comes in because, again, it's a rule. If you know the rule, you just follow the rule and you have the answer. Okay? But you have to know the rule. Okay? I want to address one more thing when it comes to nomenclature because this is a simple thing to mix up. So let's take a look at it. Identifying the main chain. That was step 1. When processing nomenclature, I would highly recommend, particularly structure to name, that you mark the longest chain. You show it. You highlight it so that you know that that is what you're referencing off of because then you can name everything else separately off of it. Okay? So if we took a look at the first one, that's the first one. Our longest carbon chain is 4. Okay? That's it. 4. So all I would ask you to do would be circle those 4 carbons. Do we have any substituents? No, so I don't have to worry about naming any other extra substituents. All I have to do is name the main chain, which is 4, which was bute. They're all single bonds. Butane, I'm done. Next one. Next one. I am losing letters. Again, we'll circle the main chain. There's 4 carbons within the main chain, nothing else to worry about, all single bonds, butane. Next one, butane again. This gets back to that whole, oh, a single bond rotating. There we go, oh, it's a different structure. The single bond's allowed to rotate. That's fine. Okay, so all of those up top, really incredibly boring because they were all butane. How about the lower left? This is what most students will highlight, and they'll say 1, 2, 3, 4, 5, 6, 7, and we have a heptane. Okay. I'm hearing people say it's 9. Okay, well, there's only 7 carbons in that straight line. What can single bonds do? They can rotate. We want the longest carbon chain. I don't care how it's drawn. I need to find the longest carbon chain. Where is that longest carbon chain? I just saw the snake too. I was going to make it a little. Okay. We now have 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. We now have a nonane. Does that change the name? Yeah, we went from a heptane to a nonane. Would we still have been able to draw the structure with the heptane? Probably, but that's not nomenclature. Okay? Just because I respond when you say, hey, you, that does not make that my name. Okay? And nomenclature, you must be very specific and reference the, and I'll put it in quotes, one name. Because there is more than one, but let's pretend I didn't say that. Okay? We could then go through, once we've got the main chain circled, identify the substituents, and name those. 1 carbon on the far right is methyl. The YL because it's a substituent on the main chain. The next one is 2 carbons. Ethyl, because it's a substituent. The last one? Ethyl, because it's a substituent. Okay? We've now probably eliminated at least 1 answer, maybe even 2, off of a multiple choice test. Okay? Again, from my perspective, that's probably enough. I will accept the 50-50 choice and just guess. Okay? Because I don't want to spend the time to figure out the rest of the stupid name for all the dumb rules. Okay? Unfortunately, because I'm now the instructor, I have to do that. Stupid rules. So we then have to go through and decide where are each of those substituents located. Okay. Well, I've got a chain. How do I number a chain? I start with 1. Where does 1 start? Top or bottom? Crap. Okay. I have 2 possible options. I have 1, 2, 3, 4, 5, 6, 7, 8, 9 in green, or let's go back over in blue. 1, 2, 3, 4, 5, 6, 7, 8, 9 in blue. Okay. Is that going to change my name? Yes. Yes. So one of those is correct, and the other one is incorrect. And guess what? Both of those answers would show up on a multiple choice test. Okay. We could reference Monday's conversation about that. Okay. So which is it? Well, we have to know the rule. What is the rule? The first substituent has to have the lowest number. Okay. So if I numbered it in green, my first substituent shows up at
4.
Position 4. If I number it in blue, 3, which is the lower number? Which is the correct number? 3. So I get 3 methyl, 4 ethyl. Sorry, I got too many numbers. Blue. 6 ethyl. Okay. That would again probably be enough. I now have my answer without actually putting the name together. Again, unfortunately, my job is supposed to go through the whole stupid freaking thing. And we can start right back at it. Go all the way from the very beginning. We had 9 carbons, so a non. Do we have any double or higher order functional groups? No, so it's an alkane, so we end with the ANE. We can underline our differences. Okay. We then need to specify our substituents. Okay. Should I start with 3 methyl, or should I start with 4 ethyl, or should I start with 6 ethyl? I will start with the ethyls at the very beginning of the name. Why? Alphabetical order. Why do we start with alphabetical order? Because some white dude said, yes, this is the way we do it. That's it. Okay, so I will start, well, with which one? 4 or 6? 4, it's a lower number, right? So 4. If I could do 4 ethyl, okay, and you guys are already jumping ahead. If I did 6 ethyl, well, that's now repeating that. I can shorten that. Instead of saying it as ethyls, I can call it diethyl. But I need to specify the location of both of those. So I got the 4, so I need the 6. How do I separate the 4 and the 6? Commas, not dashes. Again, one of the reasons why I hate grading these. Okay. Then I include a dash. So between numbers, I get a comma. Between numbers and letters, I get a dash. So I have 4,6-diethyl. Dash, because the next thing I want to put in is 3, the location for my methyl. Dash 3, dash methyl. Do I need a dash? No, it's letter to letter. I don't need anything, and then nonane. Notice with how I process it, there's lots of spaces and things all over the place. Officially, there are no spaces there. We'd have to delete those. So if I could, I think there's a cut and paste option here, but I don't know where it is. Right, we'd have to cross that out and run it all together. And we end up with 4,6-diethyl, 3-methyl, nonane. And that is now the name. Kind of makes sense? How many of you watched the nomenclature video? Good, so you all saw that and were like, that was dumb, because you did that in the video. That's true, I did. Okay? I also go through and talk about the name for the rest of them in the video too, okay? And throw in some other ones. I highly encourage you to look at that one, or that video for nomenclature, because that is on the next test. Okay? Questions on our nomenclature? Yay! Okay. I think it's 30 minutes, yeah. Watch out for sigma bond rotations. That's always going to be a problem, particularly with nomenclature. Rings make their own chain. Rings are not part of a chain, okay, which is a fun thing too. So let's take a look at that bottom structure. Okay, I did a subtle change there. In fact, let's just do that. Okay. How would I name that bottom structure? I want to identify the main chain of that structure. The bottom right. Hopefully we're tricking some people to go into doing this. 1, 2, 3, 4, 5, 6. That's 6 carbons, right? One of those carbons is part of the ring structure. Can't do that. Okay. So I have 2 carbons, I have 3 carbons, and I have 5 carbons. Which is the main chain? The 5 carbons. So this structure will get named after the 5 carbons. It'll be a pent for the 5, all single bonds, pentane. What's the shape? Cyclopentane. I can then name the substituents and identify where they are coming off of it. Kind of, sort of? Okay. Practice that. Ideally, what you will do is in your practice, you'll come across a name that you get wrong, and when you come into class, you'll be like, Mike, do nomenclature. Here's the question. Okay? Because asking me to just come up with nomenclature on the spot is not a good idea because I'm not creative. It's not going to happen. Okay? This way also, you might be able to trick me into getting it wrong. It's always fun. Okay?
So with the little side branch, you don't count the one that's part of the pentane. So it would be 1, 2, 3, propyl.
I opened the opportunity for that, so let's go ahead and look at that. So we have a cyclopentane. Should name our substituents. What's the purple substituent? Ethyl. So that one's nice and straightforward. What is, I'm going to call it the blue substituent, and I'm going to circle the whole thing. We get all sorts of nasty names that can come out of that blue section. Okay? One suggestion I heard was isobutyl. Is that an isobutyl? Yes. I also heard methyl propyl, but that's not quite right. Do you want to make an amendment? It is 2-methyl-propyl. Okay, why? Well, my longest carbon chain in that substituent is 3 carbons, so that's a propyl. In the substituent, I have a substituent. I'm not repeating that. I have a methyl. That methyl is now located at what position within my substituent?
2.
At the 2 position. Where's my numbering start?
From the ring.
Where it attaches to the ring. In this case, it doesn't matter, but it will matter in the future. You have to start numbering where it attaches to the ring. Okay?
Which is more correct?
Which is more correct? Okay, so we'll leave that. Oh man, putting this all together sucks. Yeah, putting this together really sucks. Depending on how we name these substituents, or that blue substituent, is going to mess with the order that we put our substituents into the name. Sweet. Okay? Because if we go isobutyl, alphabetically we're running as B. Yeah, that's a fun one.
The book says I, though.
It says I,
In the book, yeah, it threw me away. It said iso is part of the,
but not tert-butyl.
not church, only yeah. Yeah.
Sorry. I apologize. Love nomenclature. Okay, well that simplifies our name, so I can get away with that one. Our name will regardless be ethyl isobutyl cyclopentane or ethyl 2-methyl-propyl cyclopentane. Which of those names is more correct? It depends which system you're using. Isobutyl is known as a common name. 2-methyl-propyl is an IUPAC name. Okay. You like that word? Guess which one is officially correct? IUPAC, 2-methyl-propyl. Okay. Common names you're not responsible for, allegedly, but then you get tested on up the yin-yang. Okay. But that's the claim that gets made. Okay. So we have to be aware of our common names, but you're officially tested on the IUPAC. Okay? I don't make the rules. I really apologize for that. Well, I don't really want to make the rules, because then you'd yell at me more. Okay. But I got an easy out. I didn't make these rules. Okay? So it's a question of applying those rules and moving through it. Okay? So when it comes to nomenclature, as Mohammed very astutely pointed out, I am not the greatest source. I am adept enough that I can get the answer on a multiple choice exam. Okay? Which is really all you need to be to. Okay? If we think back to nomenclature, let's go back to the general idea on why I would have not spent any time with nomenclature. Why do we need to know how to name things? I could describe the shape without going into the name. Drew, why do I need to know how to name things?
Because it's important.
Wyatt. What I am talking about. Look at your test. Tell me how much of that is a verbal test. None of it is verbal. That's why I gave up on nomenclature. If I don't have to talk about it, I don't need to actually say the name. I can process of elimination my way through on an exam and figure it out and understand the content and kind of BS my way through nomenclature. Okay? The instant you have to talk about it is when you should learn how to do nomenclature. Some of us clearly don't follow the rules well. Okay? Make sense? Yes?
So the name for that structure is
No 2. They're both located at position 1. So it'll be ethyl 2-methyl-propyl-cyclopentane. Ideally, we would drop parentheses around the 2-methyl-propyl. Why? We want to make sure that that 2 is being referenced as a substituent within this. It is not strictly necessary because we can't have 2-methyl-propyl. That specification there would need an extra number if that number was referencing the ring. Yeah, try that logic out. Okay, but that's what's happening within it. So we don't technically need the parentheses. Okay? Practice. That's really the only thing I can tell you to do when it comes to nomenclature. So our ethane drawings, I believe we looked at ethane. Did we look at ethane? I drew that out. Line angles. So ethane, 2 carbons, 6 hydrogens. There are 2 possible or 2 easy ways that we could have drawn out the structure for ethane. And when you look at those 2 structures, are they inherently different? Would we say one of those is better than another? I'm hearing yeses and nos. Okay? Those of you saying yeses are either guessing or happen to process further through the rest of our drawings. Those of you saying no say, well, it's still 2 carbons, 6 hydrogens. How do I care how it's drawn? Okay. What we need to do is reevaluate how it's drawn and see if we can pick up a difference. So what we will do is grab that model. So I'm going to grab the one on the left. I'm going to grab that left carbon. See where my eye is? I'm going to pull that carbon out of the plane of the board and aim it at you. So everybody can easily see that, right? Okay. So this would be a case of where I would probably say, pull out your model kit. This is why we have them. Those of you watching at home, good luck. Which structure do I have in my hands? I know it's tiny, but work with me. The left one or the right one? Okay, it is the left one. Okay, both of these hydrogens are in the plane of the paper as I've got drawn. To get the right one, what do I have to do? Rotate it a little bit, and now what happens? I have the wedge coming at you, kind of up from the structure, the dash going away from you, kind of up from the structure. My 2 hands are now in the plane of the paper. Everybody see that? Okay, so let's go back to the left structure. This is what I told you to do. Okay, we grab the leftmost carbon, which is that one, the one I'm holding for you, right? Okay, so we're going to take that leftmost carbon, okay, and I want to move that out of the plane towards you. Okay. Those of you that have played with the model kit in lab probably are aware of what this is looking like, but let's see if we can get everybody else to see what's going on with this. And no, you might be like, why does he have to aim it at me? Because that's how you look at the model. Okay, so I have to kind of show everybody individually. What is the difference between that versus the other one, where we said all we did was just do that? Are we allowed to do that? What did I do?
Rotate.
Am I allowed to rotate?
Yes.
Why? It's a sigma bond. Let's do the exact same thing. We'll take that leftmost carbon and rotate it out of the plane towards you. Do you see a different representation? Yes. Okay. So what we would then do is draw that representation as we see it. So a large part of this unit is art. How do we draw what we see? Okay, so what we've got set up are both those drawings corresponding to our left and right. Notice on the left one, I've got things skewed a little bit. Why did I draw them skewed? So we could see them. Okay, but what I'm trying to represent or say is they're all overlapping there. Okay? In this view, do I now see a difference between the structures? Yes. Which means those structures in our Lewis structure, our Vesper model, are sort of different. Is one better than the other? When we looked at Lewis structures, our whole point was to do what? Draw the best one. What made it best? Lowest energy. Guess what we've got to decide now? Which one has the lowest energy? Okay. The right one has the most energy. Lowest energy. Lowest was the word I was saying. I said lowest. I don't know what you guys heard. Watch the video. Lowest energy on our, let's make sure I write that down. Our right one has the lowest. And our left one has the highest. Said it right that time, didn't I? Okay. So why? What is the difference between those two structures? What has changed? The distance between the atoms has actually not changed. The distance between the electrons in the bonds that hold the atoms has changed. What is in a bond? Electrons. So if I put two sets of electrons in the same plane, what are they now going to do? They're going to want to repel away, and so what happens? We rotate into our lowest energy conformation, where we've got the electrons as far away from each other as possible. This can be referenced as the electron repulsion, also known as a steric repulsion. Okay? We've got highest and lowest, so we have a difference. We could go through life and call one of those the lowest and one of those the highest. That's not very creative, so we become fancier, and we would need to name these. Of course, we name everything else. Take your pick. The right one. What do you want to name the right one? Each of those bonds is kind of offset from the other. They are staggered from each other. So I have a staggered conformation as my lowest energy. There are two R's? I'm going to say there's... That's close enough. Whereas what's going on the highest? Those bonds are kind of overlapping in the same place. Kind of like when the moon or the sun or the earth, one of those things, overlaps the light from the sun, and the moon becomes dark because it has been eclipsed. It sounded like a what? Oh. That is probably the first time I've ever been called a poet. We have the eclipsed conformation. So cool. The first person to at least acknowledge these and identify them and name them, of course, then gets to rubber stamp their name on top of these, and these are known as the Newman projections. Okay? So if I want to understand something about the energy of my Lewis structures, on which one is better or worse, when I can't visually see a difference between the structures, I need to change my perspective on the molecule into a Newman projection. In the Newman projection, I can better see that relationship, and I can identify which structure is better. I can then go back to the Lewis structure and say that which of those two drawings is more appropriate. The top right. Thank you for finishing that statement. Okay? So yes, the top right one is the better one because all of those bonds are staggered away from each other. Make sense? Okay. Let's skip propane and just jump straight up to butane. Okay? We already know it comes after 2, so let's just jump. Okay? If we drew a straight chain version of C4H10, notice we've got a couple formats drawn up there. We have the structural formula where we specified all the carbons and all the hydrogens, or we could have condensed that down into where we had repetition. CH3, CH2, 2, CH3. All right, remember, you're responsible for being able to interpret those structural formulas. Okay? If we again drew out this structure, we might say, well, okay, Mike, that's not all that interesting. Okay, but I could have just as easily drawn it. Okay. Which of those was the better drawing? I wouldn't know until I looked at the Newman projection. In the Newman projection, I've got 3 bonds that I could potentially look down. Okay, right? 1, 2, 3. Okay, of those 3, which one do I actually want to evaluate? The second one. Why do I not analyze the first and the third? I'd be looking at the orientation of the hydrogen atoms. Well, regardless of my orientation, are the hydrogen atoms as different as my carbons? No, there's a difference between hydrogen and carbon. Okay? What is the difference between hydrogen and carbon? Electronegativity, sort of, but not really. That's why it's a nonpolar covalent bond, so I don't really accept electronegativity. What was that? Size. Carbon is bigger. It's bigger because it has more electrons. So what am I now potentially looking at? An electron repulsion. So what I'm trying to do is identify the largest groups and see how the largest groups affect each other. I don't care about the small groups. Yes, they will contribute to the overall energy, but they aren't going to contribute as much. Does water have a London dispersion force? Yes. Yes, it does. What is a London dispersion force? How the electrons disperse through the molecule. Does water have electrons? Can those electrons disperse through the molecule? Does it have London dispersion? Yes. Do I look at London dispersion for it? No, why not?
Because it's insignificant compared to hydrogen bonding.
Hydrogen bonding is a much stronger force, so the London dispersion doesn't contribute as much to the overall interaction, and I'm more concerned about the hydrogen bonding. I'm making the same analysis here. The carbon is a larger molecule or a larger atom. I want to see how it affects the molecule, because the hydrogen's not going to contribute as much to the stability. Okay? So you were supposed to draw them. Okay. So good job. Good job. There you go. Jerome, if we looked at our ethane, we had all hydrogens around it, and we had those two relationships, right? We had the eclipsed and we had the staggered. If we went through and looked at the two drawings with the butane, I've labeled X. What are those X's supposed to be in the case of butane? Methyls, best answer. CH3 and CH3, CH3. I will still get an equivalent eclipsed, okay, but the staggered one is going to be more important to me. Why do I care more about the staggered than the eclipsed? Lowest energy. Okay. Yeah, I can draw multiple different high energy interactions, but they're high energy. I'll never react at that level. I'll react at the lowest energy. So I want to see the lowest energy configurations, and what I'll find is that there are two possible staggered formats, where the methyl groups are really close to each other, or the methyl groups are really far from each other. Okay, well, if I have two orientations, what does that mean? I need to evaluate, are they the same or different? So would we predict these to have the same energy? No. Which one's higher in energy? Let's see if I can do it right this time. Right, the left one is higher in energy. The other one is lower in energy. So I could call this higher staggered and lower staggered. Unfortunately, again, not very scientific enough. We come up with a better name. What are those names that we come up with? Well, the lower energy one, those methyl groups appear to be on kind of opposite sides. Well, what's the opposite of matter? Antimatter. What do we have here? The anti-configuration. Okay. For the purple one, okay, see this CH3? That CH3 is kind of I don't know why I had to turn around to do this. Sorry. But I did.
I think it's the answer.
No, it's worse than that. If we notice, the green one is to the what of the purple one? To the left. French for left. Is gauche. What do we call that structure? It's the gauche interaction. That's all I got.
It's actually gauche.
Fine. It's gauche. I've actually heard that, and I keep not fixing it. It's gauche. Okay. So we have the gauche interaction, okay, because that's gauchely. If you can come up with any description to help remember that, that's great.
So I read that they're not eclipsed, so it's more than 0 degrees, but it's less than 120 degrees.
So
The two molecules.
what you could start to get into is a reference for the specific rotational angle. So if we started with the fully eclipsed, so those were both CH3s up here, and we said that was 0 degrees. As I rotate the, which one are we rotating? The front carbon to the right, we would start to look like this. How far did I rotate it to the right? 60 degrees. Because if I rotated another 60, where does it end up? Eclipsed with the back. If I rotated another 60, where does it end up? Our bottom right. Another 60, where does it end up? And another 60. The equivalent of the gauche, but the other direction. And another 60. And get all the way back up to the top. Right? Yes, we can quantify that, and we can look at all of those different angles and say, oh, what's happening there? I'm not too concerned about the angles. I'm more concerned about what's happening to the structure, and are you going higher or lower in energy, and is it higher or lower in energy than what you were previously at? Right? So we will look at that. I believe it's on the next slide. But before we move to that, we've got our references. Our Newman projections, eclipsed and staggered. We have subcategories out of staggered. We have anti and gauche. Do we need to know those interactions? Do we need to know anything about energy? Yes. Guess what? This will still come back to haunt you if you don't figure it out now. Okay? And it comes back to haunt you maybe in the next 15 minutes. Right? So if we started again, this is what I was referencing. If we started with them fully eclipsed at 0 degrees, okay, would we be really high energy or really low energy? Really high energy. Okay, so we'd be somewhere up here. That's on there. We do a rotation. What happened? We go to a lower energy. Okay? It's lower than where I previously was. I don't really know anything else about that. I don't need to quantify it. It's just lower. Then I'm going to do another rotation. What happened? It's eclipsed, so it's higher. But not quite as high as the first eclipse because?
Because it's not totally eclipsed.
What is it eclipsing? Carbon and hydrogen as opposed to carbon and carbon. So yes, it's going to go higher in energy, but not quite as high. What's the next one? Low in energy again. Where low in energy? The lowest it can go. The next one. It's going to go back up to where? Which eclipsed? The second one. Because again, look at the interactions. Please reconnect. Please reconnect. Sorry. Look at the eclipsed interactions. It's hydrogen and carbon. That's equivalent to the hydrogen and carbon interactions we had over here. So that's going to go up to this point. What happens as we rotate again? It'll drop down, and then we'll go all the way back up. That's supposed to be even with the first one. It's hard to draw it out. Give me a break. Okay. What most students go through and see is not these individual steps, but the official drawing. What we're doing is now saying we're starting at one point, and we do a rotation. What happens to the energy as I move from 0 to 60? Well, at 60, it's low. What is it at 1? 1 degree. It's a little bit lower, but not a whole lot. So what's happening is I'm transitioning like this. And we go through and say, oh, wow, that's so hard. How did I have to memorize it? You don't have to memorize that. You're drawing. It's connect the dots. Okay? If you draw the dots. Okay? If you understand what's happening with your Newman projections, it's just a question of drawing those peaks and valleys, or drawing the energies, and then saying, how do I connect between them? Which then means when we go back and look at this, all of the eclipse states, you notice, are where on my curve? Describe them. I accept high. I think you actually gave me a better word. They're at the peaks. Do the eclipse states ever exist? No. What are the eclipse states? There's a name that we can give to them. They are transition states on moving from a reactant to a product, but the reactant and a product are ultimately the same thing. It's just a rotational state. Okay? So the only things that actually exist as far as our drawings are concerned are our minimums, the gauche and the anti-states, our staggered states. Kind of neat. Make sense? If we wanted to, we could really go through and draw on all of these energies, but to draw on all of those energies, what did I need to know? I needed to know all of the energies. Which sounds kind of stupid, but that's what you need to do to be able to draw on the energies. You'd have to know the values. We haven't talked anything about how to calculate it. Do you want to know how to calculate it? Thank you, because I don't know how to. Okay? All we're concerned about is their relative locations and what we can do with predicting those. Okay? Which gets us into our cycloalkanes. Okay? So we are looking at a cyclic structure. Okay? So our carbon changes folds back on itself. To fold back on itself, what will necessarily have to happen? It's kind of a weird question. So let's not officially pull it, and let's do it with the simplest one. Let's do it with the prop. What changed to go from the prop that I've got drawn up there to the cyclopropane? I drew a new bond. Okay. Is that it? Y'all having a hard time with that, huh? Maybe it would become more apparent if I did this. Is it on the black part on both sides? So you can see it on that side. I'll adjust the screen temporarily here. What changed? We lost 2 hydrogens. When else would we lose 2 hydrogens? Yes, what bond would lose 2 hydrogens? Begins with a P. A pi bond. Guess what rings equate? Pi bonds. What was a feature of a pi bond? No rotation. Can we do rotation about the sigma bonds in the ring? No. Interesting. Right? The ring tends to prevent that rotation. We can also make some other kind of observations about this. If we look at the hybridization, what is the hybridization of each of those carbons? sp3, which means the bond angle needs to be bond angle 109.5. What is the bond angle in a triangle? 60 degrees. So if I take a look at my model kit, and it's not mine, and we might need blast cards in the front, to make that, I have to kind of connect that across. The longer ones are pi bonds. I've got a problem doing that, right? What does that mean about the stability of the cyclopropane? Not very stable, because the bond angles are restricted. I have what's known as an angle strain. The structure is trying to fly open to achieve its proper angle. Okay? If we push that a little bit further, okay, let's just say that I made that connection. Okay? And because everybody loves Newman projections, let's just say it was there. It's there, right? What do you see for that Newman projection? Eclipsed. What's another issue with the cyclopropanes? We can't rotate. We've got restricted bond angle, and we're at that high energy transition state where we're not allowed to exist. Cyclopropanes have a lot of internal energy. They are dying to kind of break open. They have some special features that changes their hybridization that allows them to become more stable. Not necessary for this class, so don't worry about it. What happens if we add another carbon? Drum roll was nice, I appreciate that. Oh, I can make that one. What does that mean? It is, I don't accept stable. More stable. All relative back to the cyclopropyl. Okay? What's our Newman projection if we again look from the side? It is still eclipsed. Okay? Believe it or not, when you make this, you can actually bend those carbons ever so slightly, and what ends up happening is something more along these lines. Is that actually staggered? No, it's not staggered, but is it eclipsed? No, it's not eclipsed. What does it become? Some weird transition thing that's not gauche either, because gauche is staggered, and they come up with some new projection for it. I don't know what it's called. Okay. Just realize that your butanes will bend a little bit. We add another carbon. What's going to happen to the energy? It's going to get even lower. Okay? And again, if we look to the Newman projection, we'd say, oh, look at that. Right? It's still eclipsed. Except our cyclopentane actually has an interesting feature. We've now got enough carbons. If we look at that from the side, okay, just like the pentanes and or butanes and the propanes, they were all flat, right? And that looks flat, doesn't it? Turns out this structure will bend a little bit more. What happened to our eclipsed? It actually starts to equate towards staggered. The cyclopentane gets enough of a rotation off axis that it starts to actually become relatively stable. Okay? Or, again, more stable. Let's just say more stable. What happens if we add another carbon? Attempt to. Well, if we look at how it's drawn, we'd say, oh, it's flat. Except what happens? We'll notice that we get lots of rotation with the carbons in the cyclohexane. What does all of those different rotations mean? Look at your Newman projections. What happens as I do those rotations? Do I get different Newman projections? I get distinctly different Newman projections, which means lower energy states, which means more stable, which means name it. And we end up having to name our configurations for the cyclohexanes because we've now introduced exceedingly more stable structures. As we scale upwards and continue to add carbons in, it ends up providing so much motion that it actually starts destabilizing the ring. Okay? Cyclohexane is the lowest energy ring, followed closely by cyclopentane. Everything else is significantly higher in energy. The hybridizations affect the bond angles, which affects the stability of those structures. The Newman projections allow us to see different energies within those structures. The rotations within sigma bonds were disallowed with the ring structures, but then started to become more and more allowed as we added more and more carbons. Okay? Everything we just talked about, we spent the last 3 weeks talking about. We're using the exact same knowledge, just in a slightly more applied case each and every single time. So, what is our relationship then between these structures? Fun little test. Different means different molecular formula. Do they have... Every time this stupid slide catches me. Let's try that question again. Right? Isomers is a good bet, but we can further rotate that down or further shift that through, and we start to encounter our different types of isomers. Are they structural isomers? Structural means same, different bonding, different connectivity, we come up with a different name. If we were to name these, we have 2 methyls, so it would be dimethyl. The ring is cyclohexane, so we have a dimethyl cyclohexane in both. Where's the first methyl located? Where's the second? 2. Both of these are called 1,2 dimethyl cyclohexane, which means they're then stereoisomers, which is starting to get at your point. Because we can then further subdivide our stereoisomers down into different names and their different relationships. That's really pushing into Chapter 5. So what we're trying to do is recognize when and where we see those differences. Right? Joey pointed out an interesting feature. Where are the methyl groups located in this structure relative to the ring? They're both coming out. Okay? Also said, same side. Look at the bottom structure. Where are they? Opposite sides. Where have we referenced same and opposite before? Cis and trans. Okay? With ring structures, because remember rings are roughly the same as a pi bond, we will also introduce or reintroduce the concept of cis and trans. The relationship between these structures is they are cis-trans isomers. Okay? So we're trying to identify those relationships and see how they work and interact with each other. Would we predict them to be the same energy? I know. Why? Bottom one's more staggered? Maybe. It's all going to come down to looking at what if we're going to determine energy? Our Newman projections. So when we looked at the Newman projections for our ethane and our butane, we were looking down one carbon, okay? Because it was one carbon of our chain. What's the issue with ring structures? You can't look down one carbon. You'll end up having to look down two carbon-carbon bonds running parallel to each other. That will help you to identify the relationship between the methyl groups and each other, and the methyl groups and the ring itself. Okay? All of that is something that you're responsible for, and all of that is something that we will derive, but you'll ultimately come down to one big conclusion. Your methyl groups, or your larger substituents on a ring, will want to be in what location? Monday's lab. In the equatorial position. The axial position will end up being higher in energy. That's fun. I just mentioned two words that half the class has no idea what I'm talking about. Right? That's because we haven't gotten there yet. Okay? So we've got our... Whoa, come back here. If we built those models, right, and started to look at our structures from the side, we start to visualize different things. I know we are darn close, but I want to at least get this drawn out. Did everybody watch the model video? I know that was a long one. That was way longer than it was supposed to be. No. Okay. We look at this from the side. Dink, 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 right? Everybody see that? Dink? We have... Thank you, Monday Lab, for just calling it all out. We have a chair. We have what is effectively a lounge chair. It might be nice if we could then draw that, because guess what you have to do? Be able to draw them. So here are your steps. We'll walk through these steps and we'll end with that. We'll color code it. We want to start with the seat. Okay, so we will draw two angled parallel lines. So I will angle slightly that direction. If I want my chair to face the other direction, I will angle them the other direction. Okay? If we cut roughly, sort of, that was supposed to be a dashed line, in between, we can then move on to step 2. Pick the left or right side of our dashed line and pick your short line. So we're looking at our leftmost structure. Which side do you want to look at, left or right? Right. Right side. Which is the shorter line? The bottom. So from the bottom, I will draw an angled line down. Because? Down because it was the bottom. That's why. Step 3, complete the triangle. I will then repeat on the other side. And I've now drawn a chair. If I went through and did it with the other structure, if I sat in the chair on the left, I would be facing the right. If I sat in the chair on the right, I would be facing the left. The red, let's go through and address it over here. The red is our back on that one. The blue is our feet. The black is where we would put our seat, or where we would sit. Okay. With that, I'll go ahead and stop. I'm just going to label the other one in case someone wants to go back through and look at it. Whoops. But we are done, and I'm pretty sure the other class is going to get really mad at us because they have an exam.